Hello? Diganta, can you hear me? Hello? No problem. அந்த வால்யூம் ஏதாவது குறைஞ்சிருக்க பாருங்க. Hello? Hello? இல்லையோ தெரியலையே. அவர் அப்போ
Hello.
Okay, you can hear me?
Yeah, now I can hear you.
Oh, okay, good. So then we are all, so I will, okay. So the plan today is, I hope you got a chance to at least, read the stuff, okay? And he's going to go through that, okay? Because there was part of it was already discussed last week, but some of you were not there. So he will go through it again. So it's very important that each of you, regardless of which team you're on and which task you will end up. See, in order, yes, we will discuss that, okay, about the detailed task allocations, how we will apportion the work amongst us, etc. We will finalize once and for all tomorrow, okay? There's no going beyond that. Today, what needs to be implemented, the algorithm, etc., and that has to be what we will be discussing. And once you implement it, what the experiments that you'll be doing on will be actually doing some verification. And our plan is for you to verify some of the existing properties or the variation of them, stability property, or we are also adding in property. Let's see. Okay, that needs to be discussed as well. For that, we'll have to have a working implementation, which I'd at least like to read. So what is the best way to, by helping each other so that we'll have ideally 2 implementations, so that we will do. Okay, so today is the day that you should be asking, all questions. Not that you can't ask questions later on, but detailed questions and what you any doubts. Okay. What?
Okay, so I'll start.
Yeah.
Okay. Yeah.
So if you want, when you ask question, wait for me. I'll bring the thing to you, huh? The mic to you.
Yeah. Okay, just give me 1 second. Yeah. So can you see the PDF? Okay. So I'll just go over this PDF in some amount of detail. This is a fairly long PDF, and I don't know how much of the details I'll be able to cover. And if anyone has any questions regarding any of these sections, do ask me. Basically stop me and ask whenever. Okay.
So the context is clear. What is the overall objective is clear to everyone, correct? Huh? So in summary, we already discussed this node merge abstractions. This is a different scheme that is being proposed, for you to implement a different node merging abstraction, which we believe in some ways can be better than the simple structural node merging abstraction. And it also uses some ideas, of linear fitting from Linson. Okay, and so on. So that is, that is the idea. Once you do that abstraction, then you will use Reluplex, the Marabou, to do the actual verification. Yeah. Okay. Go ahead.
Yeah. So before going into the details of step 2 and step 3, I'll just give you one more look at the overall sort of picture. The idea is that you'll start with a network, and then the first thing that you'll do in step 1 is you'll do 3 things. You will do some simulation on it, and we'll use these results of the simulation in step 2 and 3. Right? This simulation will basically give you values that each values appearing at the output of each node of your network for various inputs. You'll also split your network. Yeah.
Yeah, the position where you're writing is obscured by some black stuff.
Okay.
Yeah, you just scroll it down a little bit. Yes. Yeah.
Yeah. So the second one is the InkDex. The first one is simulation. Then the second one is InkDex split. And the third one is some interval propagation. So when I say interval propagation, if you remember, in the deep poly lecture, we talked about that you can do something even simpler than deep poly, which is that you can just track one constant maximum and minimum value taken by each network, each node in the network, right? So that is the interval propagation that I'm talking about. So these 3 things will be done in step 1. Then what we'll do is that we will have a network. We'll have some split network at the end of this. And here in step 2, what we'll do is we will find merge group or find a merge group. Right? And then you have again a split network. Let's say this is the original network. If you call it N0, let's call this N. Then we have N comma some merge group. So then what we do in step 3 is find linear bound for the merge group. And then finally, what we have is we have N, we have some merge group, and we have some linear bound. So we merge them to get the merge network N prime.
Diganta?
Yeah.
To be technically accurate, so when you do this merge, group, there could be multiple merge groups, correct?
Yeah. So that is why there's this loop. So you find a merge group, you merge, find another one, you merge.
Okay.
Yeah.
Yes.
So there is a large scale loop like this. So you find a merge group, you merge, find another one, you merge, and so on.
Yeah. Question?
Diganta, can you just explain what the split network N is? Like what exactly is the format of that?
Yeah. So the split network. So is this place visible?
Yes.
Okay. So the split network is split according to the INCDEC classification. So if you remember, we had this this POSNEC INCDEC classification that Sir presented, right? So the split network is basically just obtained by using that INCDEC classification. So if you consider this as being your, say, original network.
Okay, so the split network will just have some classification for each neuron. So that's it.
Yeah. So you take this original network, when you split it, the number of neurons might increase. So you might have more neurons, but the idea is that each neuron will now be labeled either INC or DEC, right?
Yeah.
And this will be right exactly according to the way that Sir presented POSNEC. So we don't worry about the POSNEC neurons. We just, or the POSNEC classification, we'll only split it according to the INCDEC classification.
So that will be a transformation step.
Yeah. So is this clear? And I had presented how to do this a few classes back. So is this clear with everyone? Or I think people might not remember that as well, right? I think
like it's clear. Like I got confused by the name at least, but I got no.
Okay, sure.
Yeah,
So people do remember this, then it's okay.
I haven't uploaded that. I mean, I think I should upload it. It was discussed in detail last time, so I will upload that video.
Yeah. Okay, so this is the overall context. So now the details that this document gives you is details of this step 2, that is how to find a merge group, and details of how do you find a linear bound given a merge group. Okay, so we'll go into these two, the details of these two things. Okay. So to find a merge group, the first thing that I guess you should understand is this background on least square solvers, right? I'll quickly go over this background and also address some of the questions which Rohan had raised last time, to which I've also given answers here. What a least square solver will do is that you'll basically give the least square solver a few things. You'll give it some matrix M and it will give it a vector Y, right? So the query, the input going into the least square solver, input to the least square solver looks like this sort of a tuple. You'll have a matrix M and you have a target Y. So in my PDF, anything that is a vector is in bold. Okay, so that is the notation that I'm following. Then what the least square solver will do is that it will give you a vector X such that this value is minimal. Okay. So the output of the least square solver will be this vector X such that this is optimized. Right? So I want you to note a few things. No matter what your matrix looks like in terms of linear or non-linear dependencies between rows or columns, the least square solver is guaranteed to give you an X that will globally minimize this function. So this minimization is global and it does not depend on, rows or columns of your matrix being independent or dependent, right? It might be slightly off global due to floating point errors, but other than that, like if you ignore the possibility of floating point errors, it is going to be global regardless of what dependencies there are within the matrix. Okay, linear, non-linear, or otherwise. And I have elaborated on those points over here. So another way to think about least square solvers is that they're a generalization of an equation solver. See, if you give a matrix M and a vector Y and ask a solver to find X so that XM equals Y holds, this is the general linear equation solving query, right? So equation solvers can solve this, and they're actually usually more efficient than least square solvers. But the issue is that if such an x does not hold, or if there is no such an x, then they just give up, right? On the other hand, least square solvers will still find the x so that the equation gets closest to being actually satisfied, right? So in this sense, they are an extension of an equation solver. And like I was saying, the guarantees the solver provides in terms of global minimality does not depend on the rows of M being independent. But it does mean something in the sense that if you have dependent rows in X, in your M, especially if you have linearly dependent rows in your M, then what can happen is you can have multiple X's. So if you have some linear dependencies in M, then there can be multiple optimal X's. Right? And then the solver can return any one of these multiple optimal X values. It will never return a suboptimal value, but you don't have a control over, unless the solver tells you otherwise, you don't have control over which, which of these multiple optimal values it will return. Some implementation do provide additional guarantees, like for example, SciPy and NumPy's implementation, they tell you that, okay, it will choose the one with minimal, if there are multiple optimal X's, it will choose the one which minimizes this additionally. But again, this is not something you can configure. So you can't like ask it, okay, no, I don't want to minimize this. I want to actually give me the optimal that, minimizes something like, let's say this for some other vector, right? You can't ask something like that, for example, directly at least. So yeah, so in general, it's basically you don't have any control over which optimal value it will return. That is something that can be implementation specific in some sense. Right. So this is the background about linear least square solvers that I wanted to give. Are there any questions so far?
Yeah, you can go ahead.
Yeah. So now let's come to the 3 sub-steps or parts of this main step number 3. So the first part, basically, the first part, what it does is it assumes that you're given an output neuron. And it will use least squares and it will try to find the best input neurons and a score giving you how linear the output is in terms of the input, right? So here, for this step, what you provide as input, is an output neuron. So Y is going to be an output neuron. And what it will give you as output is the best set of input neurons and the scores telling you how good this is performing, right? Then in the second step, what we will do is we will iterate over all possible output neurons, right?
Yeah. So just so there's no confusion, I mean, the output neuron, by output, it doesn't mean the output of the network. It could be any one of the neurons in the network.
Yeah.
Its inputs are some neurons which occur before them in an earlier layer. Okay.
Right, exactly. So here by output neuron, I mean output to the merge group. Right? So if you have already chosen which neuron is going to be the output neuron of your merge group, this part 1 will give you the best possible inputs and it will also give you the score. Right? Then the idea is that in part 2, what we will do is we will use this part 1 to go over all the candidate output neurons And we will, keep track of the scores. So we will choose the one for which the score is minimal. So we'll choose the best possible output neuron. And for that, part one will also give you the corresponding input neurons, right? So part two is going to use part one and apply part one to all possible output neurons in your network. So all possible neurons that can be the output of the merge group. It will apply part one on it and it'll give it, part one is going to give you a score, right? So you're going to keep the one which has the minimal score. And part one is also going to give you the ones that will have to be the input neurons, right? So what this will do is this will basically take into input just the network. So of course, everything takes into input the network. But part two only takes into input the network. And it actually gives you the output, the best possible choice of the output neuron for your merge group and the corresponding best possible choice for the input neurons of your merge group. And of course, the score, how good the score is. Right? Finally, step 3 or part 3, let's not call them steps. Part 3, what it will do is it will take all of this. So now remember, you know what the output of your merge group is, output neuron of your merge group is, you know what the input neurons to the merge group should be. Now you need to do some sort of graph analysis to figure out which neurons will actually go into your merge groups, which will be the internal neurons of your merge groups. And this is what step 3 will do. So step 3 will take as input the network and all of these things, the output, the input, and it will give you what the merge group should be. Okay. So this is basically the structure of finding what the merge groups are going to be. So any questions at this high level? So this is basically, we'll take an output neuron and multiple input neurons as input. And it'll draw the boundary, if you will.
Okay. No questions, no? Okay.
Sure. Okay. So now let's get into the details of each one of these things. So part number 1. So here we are given a few things, right? We are given the network. We are also given the output neuron, and we want to find the best possible values of the input neurons and the corresponding score, right? So remember that what we had done even before we did step 2 and all of this, as a pre-processing step itself, what we had done is we had simulated the network, right? So we know what values appears along each one of the nodes of our network, correct? So let's fix some notation. So let's say that again, the output neuron was always going to be Y. And let's say that all of the neurons appearing before are going to be X1, X2 up till Xk. So let's go with a running example. Let's say that this is my network. And again, everything is connected to everything in the next layer. I'm not drawing the edges because it's too much to, like, it'll probably become too messy. And let's say that this is our output neuron. That is too light. This is our output neuron, Y. Okay. So then X1, X2, Xk will be all of the neurons that appear in any layer before the layer in which Y appears, right? So the X1, X2, Xk will basically be these things. So it will be X1, X2, X3, X4, X5, X6, X7, X8, X9, and K is going to here be 9, correct? So these are all the neurons that appear in any layer before Y. Now, for each one of these neurons, we will have a vector that gives us the values seen at that neuron when we had simulated, right? So when we had simulated, we would have simulated on some inputs. We would have simulated on input number 1, input number 2, up until input number K, N, let's say capital N. So then for all of these inputs, we would have seen some values. So let's say that at X1, we would have seen some value here, some value for input number 2, and up, and so on, and then some value for input number N, right? So if we collect all of these things, all of these values into a vector, this vector we will call V1 for x1. So we will have V1 for x1. Similarly for x2, we will have V2 and so on for xk, which is x9. In this example, we will have V9, correct? And we'll also have, of course, a similar vector for y. So for y, we will have Vy. Okay. So now we are in the situation where we have all of these simulation vectors and so on, right? So let's say that y is given by, the output of y is given by some linear combination of these x1, x2, of the outputs of these x1, x2 to x9, right? So loosely, let's say that we have something like this holding, right? Where the output of y is given by some linear combination. So I will here go from 1 to k, and k is equal to 9, right? Some linear combination of these vectors. And of course, we'll also have some constant term, right? So basically something like C1, sorry, not these. What I meant is the outputs of these neurons, right? So that is, so what I'm saying is output of y is basically given by C1 output of x1 plus C2 output of x2 and so on up until C9 output of x9 plus b, right? So let's say, okay. So it's given by some such linear combination where the coefficient of your combination is this C1, C2 up till C9 and b. These are your coefficients, right? So if this holds, if we do have such a linear combination, then what that means is that we will see that the vectors that we saw during simulation, the values of those that we saw during simulation, they'll also follow these linear combinations by definition, right? That's obvious, right? So we should see then that Vy is going to be given by C1 times V1 plus C2 V2 and so on up till C9 V9 plus B times one vector. Okay, so by one vector here, I mean a vector with all components being one, right? I'm basically saying we are adding this constant B, scalar B to each component of the vectors, right? So B times one vector is a vector with B in each component, and I'm adding them. Okay, and that is what I've written here. So far, is it okay? Any questions?
Yeah, you can go a little bit faster, I think.
Yeah, okay, sure. So in general, then if there is some linear combination where this, for which, you know, our merge group is behaving linearly, then this particular equation number 2 should work, right? So in particular, if we define a score function like this, in terms of the coefficients B, C1, C2 up till Ck, as being this equation or being this particular expression, then this score actually tells us how linear or how good this particular set of coefficients acts as a linear approximation for this merge group, right? So what we want to find is we want to find the best possible linear combination of the input that basically approximates the behavior of the merge group most linearly, right? So we want to find the values of these coefficients which will minimize this score, right? And how do we do that? We can do that using least squares. So to do that, let's write this equation or this expression slightly differently in terms of matrices. What we'll do is we'll pack all of these V1, V2 up till Vk into rows of one matrix M. And similarly, we'll pack these components C1, C2, Ck into this vector C, the last component of this vector will be B and the last row of this matrix will be 1. That is to account for the constant term appearing in this thing, this term appearing here. Okay. And then we can rewrite the expression or that previous equation as this, right? So now we have something that least squares can actually minimize. So if we pass this query to the least square solver now, we should get the C, which will minimize this code. And this C is the best possible linear combination of the values seen by all of these neurons. Right?
Yeah, for this sample set.
Right. For this sample set, for this particular output. It's the best possible linear combination of the values of the outputs of all of these neurons, for which will give us something closest to the values seen at the output node, right? According to the sample set or according to the simulation data that we have. So in some sense, the minimal score is going to be an estimate of how good a merge group it would be, right? So this minimal score is going to be an estimate of how good a merge group we are going to get. And from the best set of coefficients, we can extract out which neurons should be the inputs and which neurons should not be the inputs, right? So in particular, if you imagine, so let me just copy it down there.
Is there a way to how you sample this point? Because the C's are too specific to the sample.
Yeah, I don't know if you heard the question.
Yeah, I heard the question. So when you say samples, I'm assuming you mean this V1 to Vk and Vy, right? Just to understand that. Yeah, right? Is that a yes?
Yes.
Yeah, okay. So so it will be specific to this sample. So essentially we're trying to simulate it and then get an estimate from there, right? So now I guess what we would want to do definitely is make sure that these samples are as dense as possible, right? So if you have, say,
say that again. Make sure these samples are what?
As dense as possible.
As dense as possible, which means as large as possible.
Yeah, so dense and also uniformly distributed. So uniformly distributed so that you don't end up giving more preference to some parts of the input over the others, right?
So they have to be randomly generated with some uniform distribution, and then those are some implementation details, okay, that you will have to. I mean, you can parameterize that, implement with respect to that.
Yeah. And of course, it'll be dependent on the sample. So if you get a bad set of samples, if you're unlucky to get enough to get a really bad set of samples, you'll be thrown completely off. That is something that with this we cannot avoid, fundamentally speaking. And there is also there's also going to be this trade-off between, okay, if you use very large set of samples, of course, everything will be much slower, right? Because the size of your least square query, the size of M, the size of Vy depends on the number of samples. So if you use huge number of samples, the least square query might be too slow. But if you use very few samples, then the least square query is not really giving you any information, right? So there is this balancing act, this trade-off that you'll have to.
You had some experience. I mean, I had this same question to you.
So something around 10,000 samples should be fine for the least square query to handle. Okay, so the least square query should not, like the least square engine should not be, should not sweat at samples of this size, or maybe even bigger. So there is, I don't think, any reason to go smaller than that. And depending upon what kind of performance you're seeing, you can try going bigger. Okay. So does that answer your question?
Yes.
Yeah. So now let's say that we have some best possible coefficients and the corresponding best possible score, right? So the best possible score, again, this is going to be a measure of how linear things are. And in the best possible coefficients, you're going to see that the coefficients of some neurons are going to be non-zero. So let's say that these two are non-zero, these two are non-zero, this is non-zero, okay? And let's say that all of the others are zero. So what does that mean? That would mean that you only need to consider these highlighted neurons, which are non-zero, whose coefficients are non-zero, as inputs, right? You don't need to consider other neurons as inputs because they aren't contributing anything to the linear combination, right? So what we'll do is basically we'll fix some value, some threshold value, let's call it TC, and we will only keep those neurons, or we will only take as inputs or declare as inputs those neurons whose components have values greater than TC. So in this case, it will be some of these green neurons, right? The components of all the other neurons in this group, the components of this, and so on, they'll be less than TC. Okay. So this is the general idea. There is two sort of corner cases that I want to talk about. One is that if all of the coefficients turn out to be greater than this threshold value, this basically means that somehow this output is given by a good linear combination of all of these inputs, right? Or a linear combination. The best possible linear combination involves all of the inputs, right? So that is actually very unlikely to happen, right? It's not like, for example, definitely the output is not going to be a linear combination of the inputs of the immediate previous layer, right? So that is very unlikely to happen. So in that situation, what we will do is we will just ignore and refuse to do the merge. Okay. So if all of them are greater than TC, we basically don't merge. Okay. The other situation is, okay, so this should be less than yeah.
Diganta, it's right. It is right.
Oh, okay. No components evidence. Sorry, sir. Never mind. I got confused. Yeah. So if no components are greater than TC, then what this means is that the best possible linear combination is very close to being zero, right? So this can mean one of two things. Again, it depends on what the optimal value of S is. See, if the optimal value of S is bad, so if S, the optimal value of S is giving you how linear things are, and if this is telling you that things are not linear, then anyway, if you know that the best possible linear combination is very close to zero, you won't merge, right? So if the optimal value of S is, you again have to pick some threshold value. If it is larger than the threshold value, even in this case, you don't merge. So if S is large, don't merge. But if S is small, then we have an interesting situation, because then what we are getting is, at least the simulation data, what it's telling us is that, look, the output of this neuron actually doesn't depend on any of its inputs, right? So it's trying to tell you in some sense that somehow the output of this neuron is behaving very close to being constant, right? So in this case, what we would want to do is we would want to get an interval as the bound for, or a constant bound for this particular output node, right? So what we'll do in this case is the merge group will have no inputs. And this is equivalent to saying, because saying the merge group has no inputs means what? That the merge group is behaving like a constant function, right? So this is equivalent to saying replace the neuron with some constant one.
Yeah, Diganta.
Yeah.
You don't need to rewrite that. Okay.
Yeah, yeah. Okay. Yeah. I think I'll go much faster. Yeah. Yeah. So yeah, so then that is basically the two cases here. So anyway, is this clear with everyone? Any questions so far? If not, I'll move on to the other.
Yeah, you can actually save some time. I mean, later on in the thing, and in that picture that you just now drew, go up, you can actually show what is the actual group. Okay.
Yeah.
Okay, so okay, so if you want to, I thought.
So any questions so far?
Yeah, let's yeah. Okay, which.
So here, by the way, the group is going to be like this. And I'll get to why that is the case. But any questions so far? The second part is not going to take too much time. I'll go directly into the third part.
Okay. Yeah. I mean, yes, of course, for Rohan, but we'll have to carry everybody along. So, I mean, do you guys want to move to step 3? No. I think you should quickly do summarize, because there'll be some people who missed last class who need.
So they want want a summary of this part.
No. Rohan was saying that he understood. I mean, you could go. Part 3 of step 2 is where he has questions. But
Okay, sure. So, okay, then I'll maybe just go quickly over part 2. See, what part 2 is doing is just like I said.
I think for the sake of completeness, you should just say, flash what algorithm 1 is. Okay. And
yeah, algorithm 1 is exactly just what I described is written in some pseudocode. I think for the sake of time, I was thinking that I'll not talk about the pseudocodes because you can read that on your own, right?
That's fine then. Yeah. So this does given a particular output neuron, okay? To tell us all the inputs, okay? Is that
that is it. Yeah, that is.
Sorry. No. Okay. Good.
Okay. So now in part 2, what you're doing is we'll have to figure out what the actual output neuron is, right? And what it will do is that it will call algorithm 1 or part 1. So you're just going to basically you're just going to iterate over all y. So here maybe the pseudocode will actually be most helpful. So here you see you're iterating over all the y's, right? And you're calling this is where you're calling basically part 1, right?
So here, when you iterate over all y, you include the actual output of the entire network, all nodes except probably the input layer. Correct?
Yes. So here we include. So here this is all nodes except input.
Yes. Okay.
Right. Including output. Including the output layer. Okay. Yeah. And then what we are doing is we're just going to keep track of some. So we're going to keep track of some best possible score we have seen. This we initialize it to some value below which will not even do a merge. Or sorry, above which will not even do a merge. And if the score is better than what we have seen so far, then you update things, right? So this is all there is to algorithm.
Here I had one question. Okay, maybe this question to pop up in some people's mind. Now here, why can't you get as output multiple output neurons and their corresponding input neurons? Couldn't the output be multiple merge groups?
Yeah, so the only issue is like you can have situations where the merge groups might end up being intersecting and so on.
Yeah, but your algorithm picks one. Okay.
Yeah, my algorithm picks one just to avoid the situation where the merge groups might be intersecting, right? So the idea is you pick one and then you merge them, and then you don't have to worry about those neurons anymore, right?
Okay. So which means, okay, this returns only one.
Okay. It returns only one merge group. Yes.
Although there could be several minimals.
Yes.
Okay, in the optimization, it just returns one, and then that's what you choose as a candidate for merge.
Huh? Yes.
Okay.
And then we'll repeat the entire thing again to merge another.
But after you take away some of the nodes, this is the
Right. After we are done with the merge, then, the network has been modified.
Okay. Okay, fine. So there is that step. Okay, the iterate step. Yeah, fine.
Right. So now I'm going to use
That is
this
actually
picture.
not shown in your document, but that step is there. So that to see if you could get multiple merge sets, correct?
Yeah.
Okay.
So, okay. So now let's come to this where basically we have some inputs. So we know that this is part 3.
Yeah, okay. Go ahead.
So we know that we have one particular output Y, and we have these green neurons are the ones that we've chosen as our inputs, right? Now the question is, which neurons are going to be inside the merge group? So remember, wherever we draw a merge group, so if I say, for example, we're to draw it like this, right? I want the group to be such that the green neurons feed into the group. So the green neurons always appear as input to the group, and Y appears as output to the group, right?
Diganta, one question.
Yeah.
So here the green neurons are the input when the least square call was made on Y.
No, so when the least square call was made, then all of these were inputs. This entire thing was an input when the least square call was made.
So how have we classified them as green and blue?
So the green neurons we selected just because their coefficients was greater than, sufficiently bigger than TC, right? So when the least square call was made, all of these would have seen 0 coefficients. Maybe I should use a different color. All of these would have seen 0 coefficients.
Right. Yeah. Even the blue ones.
Even the blue ones, yes. The blue ones are finally the ones which are going into the merge groups, and yeah, they're also seeing 0 coefficients. Yes.
Yeah, there's nothing fancy here, is there? It's just all the paths from the input neurons that.
Yes, exactly. We're just going to make sure that all the paths that are going to go from the input to the output, they should be inside our merge group. That is all.
Is that clear?
Can you repeat, Diganta?
Yeah. So the idea is that all of the paths that are going to go from the input. So remember, we did it. So 3 steps, right? We did the least square call that gave us 0 for every neuron other than the green neurons. We did a least square call on all of these that give us 0 for every neuron other than the least square neurons, right? So now we know that the least square neurons need to be the inputs. Now we have to decide to draw the boundaries so that the input to that boundary becomes these green neurons, which means what? We need to look at all the paths going from this green neuron to the yellow neuron and select every non-input neuron on that path, right? So for example, here we have a path that is going like this, right? So that means what? Information going from green to yellow, it goes through this neuron and through this neuron. So this neuron is going to be a part of the function calculating yellow in terms of green. This neuron is also going to be a part of the function calculating yellow in terms of green, right? So then both of these 2 neurons will be inside the merge group. Similarly, there is another path that is going like this, right? So this neuron and this neuron is also part of the function calculating yellow in terms of green. So they'll also have to be inside our merge group, right?
Yeah, I think it's clear enough. I mean,
yeah. So is this okay with whoever? I think Rohan was asking the questions, right? Is this okay?
Yeah, now I understand. Yeah, thanks.
Yeah. Yeah, and the idea is that you're trying to capture all the neurons that will contribute to the function, and yeah, and of course there is an easy way to do it. You don't have to actually look at all the paths. You just have to look at if there is any, since the network itself has this layer by layer structure, if there is any neuron in layer I, then all the non-input neurons in layer I+1 are going to be connected to this. So all of them will need to be in your group. So at the end of the day, what you need to do is you need to go layer by layer. As long as there is any neuron in the layer previous to that, collect all the non-input neuron in that place, right?
yeah.
So
your definition of a merge group does not include the green nodes.
Does not include the input nodes, no.
Yeah, but it includes the blue as well as the yellow.
Yes, yes, yes. So at the end of the day, the merge group that we will get is going to be this. This is going to be the merge group. Okay. And notice that all of the green neurons.
When you iterate this process, it is that merge group that you remove. And
Yes.
then take the rest of the network and then you repeat with another chosen output neuron.
Right, right. Exactly, exactly. And of course, once we merge something, we'll not merge it again. So when we are doing it this the second time, we'll only merge unmerged neurons. We'll not merge a neuron that has already been merged.
Yeah.
Okay.
Yeah, you'll have to think a little bit more about it. Okay. So I think, whether there'll be some, when you implement the iterative process, if you remove that merge group, what if, yeah, but you'll have to do it systematically. Okay. Anyway, I'll let you think, okay, as to how you will iterate that. Okay.
Yeah, there will be some details and all of that, which
there should not be
people will have to get.
You'll have to do it systematically by going from the output, probably, to the input, not randomly picking nodes as output neurons. I feel that maybe if you pick them in some random order, whether you will, because there could be some inputs, feeding from the blue to other nodes as well. Okay, so.
Yeah. So those, so for example, this edge, right? So I think I should make this point here. When you do the merge, this point is not there anywhere else in the document. So I'll make this point here. We are going to delete all output edges coming out of merge group, coming out of this group, that are not coming from yellow, from the yellow out Y or the output neuron. Okay, so for example, this edge we will delete. And when I say that we will delete this, how are we going to delete this? We are going to delete this by replacing it with the value of the bound according to whether or not this is zinc or dex. So if this is zinc, then we will delete this edge and instead feed into this neuron the maximum value that could have come across this edge. If this was deck, we would delete this edge and feed into this neuron the minimum value it could have come across this edge, right? So all of these outputs that are leaving the group, that are not leaving through Y, we will delete. So these will delete, this will delete, so on. Similarly, this, delete all of this. Okay. So any questions so far?
Yeah, even if there are some doubts, you can ask in next class because you need to.
Yeah, next class offline anytime, right? So I think I'm sort of pressed for time right now.
Correct. Yes.
Yeah. Yeah, this is a lot.
There is some immediate question. Showstopper. Yeah.
Right. Sure. So this is basically the idea.
Diganta, you have a hard stop at 6:30. You can't go beyond 6:30. So even if there is something left over that is not able to discuss, then we'll have to do it tomorrow.
Yeah, I think 6:30 should be fine. Although I say that every time.
Okay.
So here in now let's come to step number 3. Okay. So step number 3 is now you have a merge group, right? So now you know which neurons are inside your group, which is the output, which are the inputs. You know all of these things. You have the yellow, the blue, the green, right? Now, how do you get the bound, right? So remember what we're trying to do is, again, each neuron in this thing has an index classification. So specifically, this yellow has some ink declassification. Let's assume that it's all ink, that the yellow is classified as ink, Y is classified as ink. That is what I've assumed in the document as well. Things will just, you'll just have to flip things over if it's deck, okay? So what we're trying to find is we're trying to find a linear bound for this in terms of these inputs, that is sound, right? So far, what we have is a linear approximation. Now, what we want is an actual sound bound, right? So we will use Linsin for that, and we will use 2 steps, okay? Okay, of course, there is some interval propagation that needs to be done, and you can sort of consider this as some pre-processing. This is not necessarily part of step 3. But you'll need intervals at each point to prove the soundness of the bound, right? But mainly there are 2 parts, okay? And these are in some sense sort of independent. The first part is we are going to give a rough value of the slope or the shape of the bound using an LP solver. So this is exactly like Linsin. And then the second part, we will use an SMT solver. Specifically, we will use Marabou to shift the bounding plane up and down. We'll get up some bound, we'll shift this up or down. And depending upon, use Marabou, and depending upon whether we get sat or unsat, we'll again shift it down or up to get it to become sound or become more tight. And the idea is here we'll get a verified sound and tight bound. Okay. So this is the idea. So if there are no questions at a high level, I'll go directly into part number 2. Okay. Again, in part number 2, what we want again is some bound of this form, right? We want to be able to say that the value seen at the output of Y is less than equal to some linear combination of. So here, when I say xi, notice here, so I'll just point out this notation because I think it's important. Notice that I'm using n and not k, right? So here, when I say x1 to xn, I don't mean all the inputs. I mean only the selected inputs, the green nodes, the ones where the coefficient is non-zero, okay? I'm sorry if this is confusing and confusing notation, but here I mean only those things. So I'm here by x1 to xk, I mean only these green nodes. Or if you go to the diagram I'd drawn previously, I mean only the green node selected here, right? So it will be x1, x2, x5, x6, and x9. Okay. So we don't worry about the nodes that are not an input to the merge group at this point anymore. So this guy is x1, x2, x5, x6, x9 in our example. Okay, just to be clear. That's why I'm using n instead of k. This is not k. So, okay. So we're looking for a bound of y in terms of this x1, x2, x5, x6, x9, right? So specifically, we're looking for a bound of this form, xy, I, where I is going from 1 to again n. And of course, there'll be some constant, right? So we're looking for these coefficients so that we get a sound bound of this form. So now notice that any valid bound should at least satisfy the values we have seen in the simulation, right?
I just have a kind of a question to the class here. Is it clear why those bounds are being computed? Yeah. Eventually, the merged group of nodes will be abstracted into that in terms of those bounds. Okay.
Yeah. So eventually, when you merge everything, you'll get one merged blue node, right?
That will be just, yeah, it will be those nodes will go away pretty much. Okay.
Right. So for example, here also.
I mean, this whole exercise, idea, just like the node merging method, is to reduce the size of your network. So, so that merge group, those which included all those blue nodes, will be replaced by a direct relationship between the inputs, the green, and its output, yellow. Yeah.
So specifically what you'll end up having is one merged blue node, which is connected to all of these. Right? And the behavior of this merged node will be that the output is going to be equal to this bound.
This he explained, Diganta, in the last class, okay, because they'll be equated to that bound. That's why it will be an over approximation. Yeah. So that will be either an upper bound or a lower bound, depending upon whether it's an int node or a deck node. Yeah.
Yeah. Okay. So this is basically, this is why we're looking for a bound. And since we know that this is going to be sound upper bound and this is an int node, we can always replace it and that will still be sound.
Yeah. So pretty much here, just to give, my own 2 cents worth. So, I mean, when in the original node merge abstraction also they were using, but the criteria they were using was they would merge only like colored, okay, nodes.
Yeah.
Whereas here the criteria is different. That's all. I mean,
right. Exactly. The criteria is different and it's across multiple layers. That's the main difference.
Hope is that this is a better approximation, in the sense a more precise approximation for our purpose, and that is to be, so you are to implement it and then demonstrate whether indeed it is better or not by actually doing some verification and demonstrating it.
Yeah.
Go ahead. Any
Yeah.
questions? Okay, go ahead, Diganta.
Right. So we're looking for some bound of this form, right? So now in particular, we already know that we have some simulation data, right? So we know that the outputs at each of these xi's, and we also know what the corresponding output at y should be. So if a bound is sound, in particular, it should at least be satisfied for the simulation data, right? So if you substitute the simulation data into the values for the outputs of the nodes xi and y, what you get is this equation. Correct? So now we know that any bound should be something that this equation should satisfy. So any value of any values of ci and b that actually gives us a sound bound should satisfy this equation. Okay. So now again, what we will do is we rewrite this equation in matrix form. Again, it's the same idea. Arrange VIs into the rows, arrange the C1, C2, Cn to B into the column. It's an expression that looks exactly the same. And again, what you have is you have some constraints of this form, right? So C here is this Ci's and B. So C is this vector with the coefficients of the bounds. And each C corresponds to one particular bounding plane. And now we notice that, we have to find C, and we notice that the constraints on C are LP constraints. Right? Secondly, so we already have one part of the equation figured out. We know we need some bounds, and we know that we know that means that we know we need some Ci's and B, and we know that the constraints on Ci's and B, the C vector, is an LP constraint. So if we can now formulate this as an LP query, we will have bounds, right? So the second step we'll need some sort of objective function. So see, we can have many different possible bounds. I mean, you can take some huge, very far away plane. That will still be a good enough bound, right? But what we want is a tight bound. So in particular, what we want is a bound so that the volume underneath the bound is minimum, right? So what is the volume underneath the bound? See, the bound is given by this expression, right? And we know that xi, each one of these xi's, because of the interval propagation, we know that it's going to be in some interval Li ui, right? The outputs of xi is going to be in this interval Li ui. correct? So the volume under the bound, that is what we want to minimize, right? Because the smaller the volume underneath the bound, the tighter the bound is, right? Visually, if your bound is something like this, and then the volume underneath is this particular area, and the more you minimize this, the lower your bound goes essentially, and the tighter it becomes, correct? So if you want to minimize the volume underneath the bound, then we want to, in some sense, minimize this expression. What is this expression? This is just taking the integral. So the volume is going to be given by an integral, right? The integral is going to be over all the inputs that you have to the bound. So you're integrating over this axis, and the integral is going to be within this intervals, right? So your xi, for example, goes between, so x1, for example, goes between L1 and U1. So that is your x1 going between L1 and U1. X2 is going between L2 and U2, and similarly up till xn going between Ln and Un. And you're integrating the actual expression of the value of the bound, right? The value given by the plane. So this integral gives you your volume. I claim that if you expand out and simplify this integral, you get this particular expression. Now, this expression might look complicated, but for now, notice that this is linear in C. This is the key fact, right? Because what are you doing? You're taking B, multiplying with some constants, right? These Li's and Ui's for our purposes are constants. So you're taking B, multiplying with some constant. Taking each Ci, and each Ci is again getting multiplied with some constant, right? Again, some huge constant in terms of Li's and Ui's, but constant. So it's a linear expression, correct? So if this is linear in C, this now gives us an objective function. So this is going to be our objective function for LP, right? And this is basically going to be the LP query now. The LP query where the constraints is going to be given by this. The objective function is going to be given by this. You solve the LP query, you will get a set of, you'll get a C vector giving you the set of bounds that you're looking for. Okay. And this is what is happening in this pseudocode as well. So if there are no questions, then I'll get into the second part of the this step 3. Any questions so far? No? This is all clear?
Yeah, no questions.
Okay, sure. So now let's get into the second part of this. And here, what we want to do is, see, now what we have is by the LP query, we have gotten some bound, which at least is good in the points that we have simulated, right? We still don't know whether it's globally, like it's actually good or not. We still don't have any soundness guarantee, right? So what we do is we will...
Yeah, soundness guarantee for all inputs. Okay.
For all inputs, right?
For the sampled inputs, I guess it is...
Sound, yeah. But for all inputs, we want this to be sound, right? So what we'll do is we will actually take this. So we have some bound, some Ci's and B, and we can phrase a Marabou query for this small merge group, right? So again, if I borrow this picture that I've been taking, right? What we'll do is we'll take the merge group out. So that means we'll have this, and finally Y, correct? And we have the other, the inputs to the merge group coming in and so on. So what we want is we want to phrase a Marabou query where we encode this part, the merge group part of the network into Marabou. We encode the fact that this is going to be, we encode intervals for all of the inputs into Marabou, right? So we encode the fact that, for example, here these inputs are also coming in. So these inputs will also have to be here. Right? So let's make them green. We encode the fact that these are xi's belonging in li, ui. We encode that also into Madabu, right? For each one of these inputs. And finally, we encode the fact that this y is going to be less than equal to, or should be less than equal to, the bound that we have found. Right? So we encode that also into Madabu, right, as a post condition. Which means what we actually send to Madabu is the negation. So this hopefully is clear to you by now. So we encode all of this into Madabu, and what that will basically give us is a Madabu query, which if it comes sat, that means that the bound is unsound. Whereas if it comes unsat, that means that the bound is sound. Right? So now we have some candidate bound from LP. This is coming from LP, gives us this. And this we paste into the Madabu query here. Right? And if it gives us unsat, then we know that the bound is sound, and in some sense we are done. Right? We can still try and find tighter bounds, and we'll look at that, but we're done. But if it's not, we have to somehow adjust the bound a little bit, and then hopefully ultimately get a sat bound, right? So we can basically encode the fact that the bound holds this soundness check into Madabu and do multiple checks to get the tightest possible bound, right? So any questions regarding the sound, checking the soundness of a given bound using Madabu? Is there any question? No?
Yeah, this will, as you note, may require multiple calls to Reluplex / Madabu, each time relaxing or
yeah, but for checking one given bound, it's just one call. This, and you encode it like this and do one call. Yeah. But yeah, you will have to check multiple candidate bounds, and so there will be multiple calls. Okay. So if there are no questions, then let me come to this algorithm where I show you what are all the calls are, right? This encode Madabu that you're seeing, this basically does what I was telling you in that diagram, where it encodes one particular bound, right? So what this will do is this will not change. So here, we have gotten some Ci, B from LP, right? We are not going to change this. So this doesn't change. At this point, what we're looking for is we're just going to shift B up or down until we have a tight bound. Right? So this algorithm again works in sort of two phases. There is this phase 1, and then there is phase 2. Okay. In phase 1, what we do is we check with, we do a preliminary Madabu query, right? We take the existing bound that the solver has given us, and okay, we just check whether it is satisfied or not, right? If it holds, then what we're looking for is we're looking for potentially a tighter bound, right? We're trying to see if we can do better than this. So what we will do is we will half the bound every time and then query again. If it still holds, half again, right? So reduce by half again. And then query again. If it still holds, reduce by half again, and then query again. Okay. Similarly, if on the other hand, the initial bound does not hold, then what we know is that, okay, the initial bound is actually not good enough. So we have to increase B until the bound is, until we get a sound bound. We have to at least get a sound bound, right? So then what we do is, again, we will double it, check, again double it, check, again double it, check, until and unless the bound begins to hold, right? So this is what we do in phase one. If for a particular value of B, it was sat, then we half it again, until we get an unsat, right? On the other hand, if for the initial value of B, it was unsat, then we double it again until we get a sat, right? So the end of phase one, what we have is, we know that we have one value of B for which the bound is unsat and one value of B for which is sat, right? So we know that the tight value of B, the value of the smallest value of B for which we can still get the, the bound being holding, is going to lie between these two places, right? It's going to lie in here or in here, right? So we set this to the upper bound of B. We set this to the lower bound of B, or in the other case, this is the lower bound. This is going to be the upper bound, right? And then in phase two, what we will do is we'll do a binary search. So now we know that, okay, look, we know that up here things are valid, up here things are invalid. Let's try the middle, right? If it becomes valid, if the middle becomes valid, then we'll shift the upper bound down here. If the middle becomes invalid, then we'll shift the lower bound up, right? And in this way, we'll keep doing a binary search until, the upper bound and lower bound are too close, at which point we'll stop. We'll stop and we'll pick the, we'll basically return the upper bound that we have found. Okay, so we'll return this. So this will be BU, not B. Okay, so this is basically the algorithm. Any questions? So firstly, you take the bound. If it's sat, you try and you keep reducing it. Like if it holds, you keep reducing it until it doesn't, and then you can have an interval in which you can do binary search. If it doesn't hold, you keep increasing it until the bound holds, and then you again have an interval in which you can do binary search. If this is complicated, even just phase one you can try, but instead of doubling, you can just try subtracting a constant or adding a constant here. But yeah, this is basically the idea. So is this okay? Any questions? Do read through this. Most of what I talked about is explained. Some things aren't, but most of it is explained. I'll upload this. This will be there on YouTube. You can refer back. But any questions right now?
No.
Okay.
See, what I suggest is, I'm sure this is a significant material for you to digest, okay? So I think as, separate teams, you have to, between now and tomorrow's class, find some time to discuss amongst yourselves, okay? And then try to, each of you read, discuss, and then come up with any list of questions and doubts that you have. Additionally, more importantly, in your own kind of work, we kind of make a list of what are the tasks we will, that you will have to implement. If you were to, as a team of 3, we're going to be implementing it yourself. I mean, as a team, I'm saying, okay? And get an estimate of, in the 2 weeks or 3 weeks that you have, how you would apportion if you were doing it, just amongst the 3 of you, okay? And we will discuss. We'll also do that and have an estimate, and we will, come up with some we'll align amongst ourselves as to how we could help you to, complete the task. So we will have ideally 2 implementations, or maybe 1 working implementation. Yeah. Okay. So, but I want you guys to spend some time between, take the time between now and tomorrow's class, so that you can, without any being shy, just say, oh, this is too, I mean, but you'll have to first estimate what the effort is and what you think, if you're able to accomplish it. Yeah. And what the challenges are. Yes. Okay. Do you want to add anything, Diganta?
No, I think that's, yeah.
Yeah, because tomorrow we will decide the tasks. Okay. And, so you can contribute to it. We will have our own view of what the tasks are, and there's already some 6 algorithms, okay, which you'll have to implement. Yeah. And additionally, you will have to, once you test it and so on, you will have to run some experiments, which is really doing some verification on examples that we will, tell you what to do. And in order of how challenging it is, you may want to list, the tasks, okay, which you think is more difficult and less difficult and so on. And we'll come up with our own view what it is. And if we ask you to implement each one implementation per team, what do you think is, if you can do it or not? Okay, and if you think it is going to be hard, you will have to give us some feedback as to where you think is you need help. Yeah. And then we'll see how we could help you out. Yeah. Okay. Any other questions?
So shall I stop sharing?